Hi everyone. Welcome to the introductory course on Twistor theory. My name is Rafael. I'm from the University of São Paulo in Brazil. I work in string theory, twistor holography, and some of these fancy little words that for some of you doesn't mean a lot of things. But hopefully by the end of this course, I will be able to provide you some of the tools to understand some of the words that show up in the literature, in the more modern literature on scattering amplitude, celestial holography, string theory, and all that kind of things. Um, so my goal here is pretty much to not give like a completely thorough account on Twistor theory because it's been for some of you that have already seen something that's about it was they were introduced by Penrose in 67. So it's been well over 50 years since since this construction has been presented, and they were originally intended. They were introduced by Penrose in the context of GR, and specifically they were introduced to study what are called self-dual and anti-self-dual solutions to the linearized Einstein's equations. Okay, and but the thing is that they as we will probably see by the end of this lectures, there are some rather philosophical problems about this construction in the sense that it is quite non-local. The relationship between a twistor theory, twistor space. So the relationship between twistor space, which I will define by the end of the lecture, and space-time is non-local. And this is quite interesting from a mathematical point of view and from more theoretical point of view. But by the time when these constructions first came about in the literature by Penrose, they were seen as somewhat unphysical objects and somewhat not very interesting from this point of view because of these kind of problems. But the thing is that they made a comeback around, I guess it was 2004, in works by Wheaton, built upon Nair, in which you could pretty much combine this construction of twistor spaces and string perturbation theory to actually recover the trio level amplitude of n equals 4 super Young-Mills. So in the context of holography, essentially. So n equals 4 super Young-Mills and string theory. So I will also present somewhat of an older development using this twistor theory that actually motivated Nair to come up with the use of twistors in scattering amplitudes, and then led Witten to actually make this construction. So the point that I want to convey here in this somewhat short introduction is that there's a lot of things that you can talk about in twistor theory, and it's pretty much impossible to give like a full account of everything that we could possibly have. A very interesting review article that I did not include in the bibliography on the website, but I can write it down here for you guys. Is so for an extensive review, you can check out. Let me put the archive code 1704. So this is a review by Atia Dunajski and Mason. And you can pretty much find a lot of things that it is a somewhat it is a kind of a more recent review. It's from 2017, but it has a lot of information that might be useful for you to understand how twistors come up in different areas of physics and mathematics. So the goal in these lectures will be to present some of the basic constructions, some of the basic definitions of twistor theory, show you how to kind of play around with them, how to recover some of the constructions that we have in Minkowski spacetime. So I'm not going to go a lot into the use of twistors in curved spacetime because that's a more complicated issue. But I might at some moments I might show some of the ways that these things generalize to more general spacetimes. So yeah, and at some point in these lectures, I am going to actually by the end of each lecture, I am going to send you guys or post it on the website the lecture notes that I have, not these handwritten ones, but ones that I LaTeXed, and so that you can see some of the exercises that I propose over there. And I might use one of the sessions, one of the classes to actually work out a couple of these exercises or serve as a like a TA session, like an office hours kind of thing for those who are tempted to do the exercise and are having trouble or something like that. So yeah, and if you really want to get ahead of the lectures, we're pretty much basing on Tina Adamo's lectures, which I've included on the bibliography on the website. So if you want to kind of see where we're going ahead, where we're getting at with these lectures, you can probably check over there because I'm following pretty much the exposition over there with some notational differences and some emphasis in some other aspects. So, are there any questions about the course or how we're gonna follow this? I guess not. So let's start. Let's properly start this thing. So the first thing that I want to talk about are spinners and twistors. So we'll see that twistors have a very close relationship with spinners, and it is somebody asked assignment. So I am not going to give you an assignment as meaning that you need to turn it in. I will give you some, I will provide the lecture notes and they contain some exercises. And if you want to, make sure that you're following up everything, it might be a good idea to try to look the exercises. I've pretty much divided these exercises in like two categories. One of them is if you take a read at the text, there will be some points that I'm saying something, and then I write down in parentheses like exercise like this. These are what I call like fast food kind of exercises. They're a good option if you're really hungry for something, but they're not a very healthy. They're not a very healthy option in the long term. So you can try to you can do all of them so you can complete fill in the details on the text. But you should also attempt like the the exercise that I've left on on the written notes. Um, if you want more exercises, you can check out Hug and Todd, which I've put on the literature part in the website. This is a very good book. It's very compact. It's very easy to follow. The notation that I'm using is a little bit different. The notation is a little bit more modern, but you can pretty much follow. You can find a lot of exercise over there, and some of them even have solutions if I'm not mistaken. So it's a good place to take a look. So I'm not gonna grade your assignment or anything like that. But I expect that people will attempt to do a couple of exercises in order to follow well the lectures here. Um, okay, if there are no more questions about this, so let me talk a little bit about spinners and twisters. So let's recall how we do the construction of spinners in Minkowski spacetime. So the first thing that you should remember is that a crucial part of Minkowski spacetime is the isometry group, which is SO13, which is also called the Lorentz group. Here I will be kind of loose on what I mean by the Lorentz group. You can, if you're a little bit more, if you want to take a little bit more careful, you can think of it as the component that is connected to the identity, the part that only has continuous transformations. So you're pretty much excluding parity transformations or reflections. So if you look at this group of what this group actually is, it is a set of matrices. So it acts on R4 by leaving this bilinear form invariant. So we construct on R4 with this bilinear form, which pretty much means that I'm taking x0, y0 squared minus x1, y1 squared minus x2, y2 squared minus x3, y3 squared. So you can, if you want to recover that usual notion that you have on using differentials, differentials, you can think of this as a kind of displacement and write it as a dx, which is like an infinitesimal displacement of 2 points on R4. And you will recover that usual line element, the s squared. But the point is that you can write this in terms of the um, in terms of these in terms of the components of the metric. So it's something like this. Yes, you're absolutely right. There's no squared on this. I was already thinking about the x with itself. Thank you. Let me just take this out. So yeah. And where these components, this bilinear form is given in terms of a metric of a matrix. Let me just see if there's another question in the chat. Okay, no, this is this. So the Minkowski metric, yeah, we will use this convention. Disclaimer, I do not like this convention. I prefer the other one, but this is the most recurrent one when we're talking about spinners in the literature. So it's the one I'm going to stick because a lot of the hard part of this is comparing different conventions and different notations. So I prefer to use the ones that are more commonly used, even though I don't agree with them. So we want to define the matrices which act on R4 and preserve this bilinear form. So we will be interested in matrices lambda, which will define our Lorentz group, such that um, when you act with them on this bilinear form, beta y is equal to um, the bilinear form itself. So there was another question in the chat. H represents Hilbert. No, I'm not talking about Hilbert spaces. No, this is just basic special relativity. No Hilbert spaces here. So this condition holds if and only if you act with the transpose of these matrices on the metric tensor, it leaves it invariant. So this is something you all should know. This is something we see in like day one of a special relativity course. And if you've taken general relativity, you've seen this again. And this is pretty much the simple definition of a Lorentz group. Now the thing is, the spinner thing enters when we do the following construction. So given some vector v in R4, we can construct a 2x2 Hermitian matrix um, by doing the following. So if V is given in terms of components as V0, V1, V2, and V3, we can construct uniquely a matrix, which I will denote using these components with these indices by just contracting them um, with the Lorentz indices. So we're sorry, this should be an A. So I'm using Latin letters to represent the Lorentz indices, and I'm using Greek letters to represent what we will understand as the SL2C indices, the spinor indices. There's another question. We're restricting to using generators as SON groups, or can a generic element be taken for the transformations? I'm not sure if I understand the question, but no, I am defining the Lorentz group as a set of transformations that leave this bilinear form invariant, and certainly we have a SON, an SO3 as a subgroup, which is just the rotations. So the Lorentz grouping includes rotations and both the spatial directions and time directions. So yeah, certainly a spatial rotation, which is given by the SO3, is included here. Not really sure if that was your question, but um, yeah. Okay. So we could contract these with these Pauli matrices, which you've probably seen in like a basic quantum mechanics course. There's like a normalization here, a square root of 2. And these allow us to, if we write down explicitly the matrix form of this, you could check this yourself if you plug in uh, the Pauli matrices plus the identity. You should get something like V0 plus V3, V1 plus I V2, V1 minus I V2, and V0 minus V3. So all of these all of these entries, all of these numbers here are real numbers because we're pretty much picking a vector from R4. But the fact that we introduced here this I factor means that we're not talking about a 2x2 complex 2x2 matrix with complex entries, which you can check that it is Hermitian. It's pretty straight. And these indices, alpha and alpha dot, it is convention that we say that they run from 0 to 1 and 0 dot to 1 dot. The dot is just to understand that we're talking about, we will understand these as being indices in different representations, which will be two copies of SL2C, as we will see forward. But you should read these as just saying which column and which row you are, like a basic matrix thing. So now an interesting thing is that if you compute the determinant, so if you compute the determinant, you find that it is that twice this determinant of V alpha and alpha dot is equal precisely to the I-line element of the vector with itself. So if you compute the this bilinear form that I showed here earlier with these vectors, with the components of these vectors, you should get is precisely twice the determinant. And the factor of 2 comes from this normalization factor over here, essentially. Okay, so we found a different way to represent what we will physically interpret as the invariant interval that we have in special relativity. Because, as you might recall, we had that, ds squared is equal to at the AB dxa dxb. And if you compute this, if you consider these vectors as being these displacements in R4, you find exactly this. So we found a different way to obtain this invariant interval in terms of 2 by 2 matrices. So how do we consider now the transformations that preserve this thing? Meaning, how do we reinterpret Lorentz transformations in this context of 2 by 2 complex matrices? Well, of course, if we wanted to preserve this interval, we now want to preserve this determinant. So we will consider transformations. So consider transformations of the type. So I'll have my VA alpha dot. I will do a transformation to a V tilde alpha dot, which will be given in terms of matrices, which are given by these. So the determinant has the good property that is cyclic, meaning essentially that if you have the determinant of 3 matrices, these are equal to the determinant of any permutation of these matrices, cyclic permutation of these matrices, which is equal to BCA. So we can use this to infer that we must have that this T bar, this matrix T bar, it must be exactly the inverse of this matrix. And if you interpret this T bar as being the complex conjugate, the conjugate transpose of this matrix, so we are led to consider unitary transformations. Hence, now the Lorentz transformations will be elements of a group called SL2C. Which means there are matrices which are essentially matrices that when you apply this transformation, they preserve the determinants. So their complex conjugate is equal to their inverse. So we are let's consider these as our new Lorentz transformation in this context of where we consider now, instead of considering the vectors, we now consider these kinds of matrices. Okay. So the next step then is to try to understand the consequences of these. Just for the people that are a little bit more of maybe a group theory aficionados or interested in this kind of things. This statement that I just did, it just says that this kind of thing, this map over here of these two groups is a homomorphism, is a group homomorphism. And which is not an isomorphism, but we can construct an isomorphism if we consider a quotient of this group by the identities. And this essentially means, so we have plus an identity and minus an identity. And we define this as being what is called the projective special linear group in two dimensions. So this is an isomorphism. This quotient over here, it basically comes from the fact that the kernel of this transformation is given by these elements and by something called the fundamental um, homomorphism theorem of homomorphism. If you take the quotient, if you take a group homomorphism and quotiented the image by the domain by the kernel, you get an isomorphism. So if you want more details on this, you can check out Nakahara. So so pretty much in the beginning. And yeah, so this is a little bit of a detour. So when I'm saying that we're working in the Lorentz group, and I'm referring to SL2C, I'm being a little bit loose with my language. I'm not being completely precise because we should be actually thinking about this group as the Lorentz group, not the SL2C. Okay, I hope that's clear. Okay, so we saw that we can pretty much let me just use the notation that I was using before. Okay, alpha beta, beta dot, alpha dot, beta dot. So we've seen that this is the Lorentz transformation. So originally when we were thinking about SO 1,3, we were thinking about the Lorentz transformations as acting on vectors, on the which are elements of R4 essentially. So the question is, so the question, what are the elements, or better said, what are the vectors on which SL2C acts on? Yeah, there should be a bar in the second one. Yes, thank you, thank you. So what are these vectors? So this is what will give the origin to the notion of a spinner. So the first thing that we should consider is that if you should recall, so recall that if eta AB, so for a vector, we have this condition holds. So you take the inner product of using the Minkowski metric and it vanishes. This means that V is null or like. So it's a like vector. It's something that lives on the border of the light cone that defines the causal structure of your space-time. So we have this condition. Now, if this thing holds from our let me copy the correspondence that we had here before just for clarity. So if this holds because of this thing over here, we have that the determinant of V alpha dot is equal to 0. Now, this can only, so V alpha alpha dot is a 2 by 2 matrix. So we all learned in like first course on linear algebra that if you have a matrix with a zero determinant, this means that the one of the lines or one of the columns of the matrix is a linear combination of the other one. So the rank of the matrix drops by one, at least one. So here in our case, since this is a 2 by 2 matrix, this condition infers that it has rank one. And it is a good exercise for you to warm up to show that every 2 by 2 matrix with rank one can be written as so I'm already going to write down this null. So understand null here as being so this as a matrix that has the determinant zero. So it means that it can be written as the outer product or the external product, depends on where you're from. You can understand this, of two vectors, which essentially means I'm not taking the inner product of two component vectors. I am taking something like a column vector, a 2 by 2 column vector, times another row vector. So this is a 2 by 1 matrix. This is a 1 by 2 matrix. The result of this should be a 2 by 2 matrix. And if you do this with these guys, you can show it is an if and only if condition, meaning that you can start from this for this thing. You can construct a matrix by this, and you can show that the determinant is zero or that it has rank one. And you can show that a matrix that has rank one can be written in this way. So this is a good exercise for you to try to think a little bit about. Let me see if there are any questions. Should there be? Yeah, this was the previous one. Okay. Okay, so far so good. Basic things. Now, so if we can write the null vectors as this way, we are led naturally to consider, at least for null vectors, objects of this type. So what are these? These are two component Weyl spinners. And because we are considering like the outer product, we are led to consider these two indices. Let me circle them. These two indices as actually being different representations. So the indices are indeed in different reps of SL2C. SL2C, yeah. So in fact, so we are led to consider things like we say that these vectors live in SL2C, comma SL2C, because you need two of these indices to describe one vector in the in Minkowski space-time. So these things are called Weyl spinors. They're two component. You can think of them as just being complex vectors with two component complex vectors, but they are related to the vectors in Minkowski space-time. So these are the things that SL2C acts on. So you might this might have been obvious. You have these 2 by 2 matrices which are in SL2C. And sorry, let me do this a little bit better. So SL2C. So we have these 2 by 2 matrices, and they should act on stuff that is let me use a different letter here. They should indeed act on something that is like a two component complex vector, and we discovered that these are indeed spinors, and they have a relationship to the points in space time. So it's not just you could have just ended up with a representation of the Lorentz group, and the thing that the matrices actually act on might have not been physical, but the thing is that at least we can write the null vectors as being combinations of these spinors, so they're pretty physical. So yeah, I hope that this is clear. This should be somewhat of a a review from quantum field theory. So if there are any questions, I'll take them now while I drink some water. Okay, since there are no questions, um, we would just point out that sometimes this alpha prime index is referred to as a positive chirality. So let me write this in terms of the spinor. So a spinor that has only one dotted index, this is a positive chirality. While a spinor that has only the alpha index without a dot is called a negative chirality. Okay, good. Um, so we will be interested in working in what will eventually be C4, which will be a complexified Minkowski. Right now we're working in C2, which is just the space of these vectors which are complex, where A and B are complex numbers. And we would like to, translate everything that we have from Minkowski spacetime from uh, R4 comma eta to this in space, which means that we need to find something like this, like a Minkowski tensor on this. So the vectors live in C2 and the transformation is SL2C. Yes, that is absolutely correct. So sorry, let me just see if I read this correctly. Yes, yeah. The vectors, yes, the vectors living in C2 and the transformations SL2C. That is correct. But SL2C acts on the elements of C2. That's the point I'm trying to make. So yeah. Okay, so we want to have some sort of tensor that would in a very crude and kind of dumb way raise and lower indices. So we want a tensor to raise and lower the indices. And we do that by declaring, by using the Levi-Civita, um, what lives in SL2C across SL2C, this vector over here, which anything that has two of these components. So for instance, this guy over here lives in SL2C cross SL2C because it has two indices, two SL2C indices from opposite chiralities. Okay. So we want this kind of tensor to raise and lower the indices, and we use this by the Levi-Civita. Oops. So we have the Levi-Civita into D, which is just epsilon alpha beta, which you can represent as a matrix as being 0, 1, minus 1, 0. And this is declared to be the same as the opposite one. So each copy of the SL2C has one of these what is these invariant tensors. So it's I leave it as an exercise as well, which is show that this is invariant under SL2C. So it's a pretty easy thing to do. You just need to consider the correct action of the SL2C group, which is by something like um, A dagger B8. So this will be the action of the group. It's not just a simple multiplication of the elements of SL2C by this epsilon tensor. All right. So together with this, so let me copy this to the next page, since we're going to still talk a little bit about this. So these come equipped with inverses. So we define the inverses by these relations in which we contract the indices. So epsilon gamma beta, we will do this, and epsilon alpha beta. And if you take the trace, essentially, this is just 2. Okay. Now, something that you should be very mindful is that this tensor over here, unlike the Minkowski metric eta, it is not symmetric. So this is easy to see. You can just switch on the components of this, and you can pretty much convince yourself that this is true. So because we have something that some people call this skew symmetric or anti-symmetric, because we have a relationship like this, we need to really be careful with the conventions that we have on where we're placing the indices, where we're contracting, how we're actually raising and lowering the indices. So the convention that I'm going to adopt, I think I'm pretty sure that it is the most common one, which is this convention. So convention. So if I have a spinner with a lower index, I define this as being just something that is raised times the least invariant tensor here on the right. While if I have another spinner with a raised index, I can define this as being this given by this relation. So the convention is kind of like we have like something like a lowering to the right. So this is sometimes lowering to the right. While this is kind of this is the other way around. So this is kind of like the convention. Sometimes this is called raising to the left. So I invite you, I invite you guys to try to play around with these indices, trying to construct invariant stuff and try to verify the quantities that you have. And as a rule of thumb, so kind of like a rule of thumb, every time that you have some sort of a tensor with many components, let me put like A, B, C. Something like this, you can translate this into to this component spinning language by substituting every Lorentz index that you have by a pair of SL2C indices, while indices. So this quantity will be transformed into something like this. So an alpha alpha dot, a beta beta dot, and then a gamma gamma dot. So you can play around with some of your tensors, not being too worried about the form of them, and you can try to play around and try to see what you have to multiply this tensor with to raise and lower its indices. So there's another question. Why matters the position of the Levi-Shifted tensor? Is it just a convention? It is a convention, but the thing is that because the Levi-Shifted tensor is anti-symmetric, If I were to write this thing here the opposite way around, something like this, alpha beta, this is minus a beta epsilon beta alpha. So you have to be so you have to be careful with the position of the indices. You cannot just change them around when you're contracting because of this anti-symmetry property. So if you're not convinced about this, I invite you to write explicitly. You can for instance, you can try to write a beta as being some sort of A0 and A1, and then multiply this by this by the metric, and try to play around with this sort of identities. When in doubt, try to write things down explicitly in terms of matrix forms and with the components explicitly. I understand. Thank you. How can the derivative achieve the lower indices? Usually in differential geometry, we have that the lower indices has a relation with an internal product that depends on the metric, the true form. That is exactly what is going on here. This is a sort of a metric, an invariant metric is a true form on the acting on as an element of SL2C which acts on C2. So you can as I said before, I'm just treating this as being some kind of a dumb thing, which is just raising and lowering indices. But you should remember from general relativity that we have the convention that things with lower indices and upper indices, you can interpret them as being vector indices or one-form indices. So they're pretty different objects. And the isomorphism that you have between vectors and one forms is given by the metric tensor. Something very similar happens over here. So you can also work out that if you contract something with a lower indices, something with an upper index, you should get a scalar. Which just means that one of the things that is acting on the other is a one form, and the other one is a vector, because one forms are things that takes vectors to numbers. So yeah, your question is valid, but I'm trying to be a little bit simpler here to not carry too much notation. Okay, more questions. Yeah, thank you for the question. All right, so okay, so now I just want to I want to introduce it. So let me just following this kind of rule of thumb we had before, the invariant interval would be something like a at the AB XA and XB, and now in this kind of language we will write this as being essentially epsilon alpha beta, epsilon alpha dot beta dot dx alpha dot and dx beta and beta dot. So I just I just obtained the indices, and now I need two copies of this invariant tensors, because as I said, as somebody asked earlier, these guys over here, they carry two SL2C indices. So these guys live in the space where SL2C cross SL2C axon. So this axon, so acted by this. Okay, so one final construction that I want to do here is the inner products. So SL2C invariant inner products. So by some of the questions over that I'm receiving here in the chat, I see that you guys are familiar with these the nomenclature that we use in mathematics for an inner product. So I'm pretty sure you guys know what is the usual definition of an inner product. But here we're going to be a little bit more variant inner product. We're going to be a little bit more general, because we're not considering, because again we're considering anti-symmetric tensors. So we will, for instance, end up with inner products that are not positive definite. And this is something that is pretty much easy to see. So don't be too bugged about upon the name of a new product. Don't try to keep showing that this thing follows the usual definitions of an inner product that defines a Hilbert space and stuff like that. So we just wanted to do constructions that you can contract to spinors and get so sort of a scalar. So we have actually two options. So number one, which is usually represented by angular brackets. So I have two. Let me just let me just be more complete. So consider kappa, which is with components kappa alpha, and you also got omega and omega with a lower index. And we also consider kappa tilde with components kappa tilde alpha dot. And same thing for omega tilde with omega tilde alpha dot lower. So I'm just saying this because I want you guys to think of each one of the so things without tilde as living in one space on which one of the SL2Cs act upon, and the other one which carries these alpha dot as being a spinor on the other SL2C. So we can construct number one a inner product which is given by a kappa omega, which is on one of the copies of the SL2C, which I will simply define as being the contraction of this, or something like this, which you should write as a kappa alpha omega beta with epsilon beta alpha. Now, following the I guess like contravariant and covariant. There was a question here. I'm not sure what do you mean, what exactly you think is contravariant, covariant, but I think you're talking about the definition of, you know, a vector as a contravector and one forms as being the covector, stuff like that. Yes, that's kind of the idea that we're going for here. But just as somebody remarked as a little bit earlier about the importance of the indices. Sometimes you know, people will write this kind of inner product here on switching these two indices, which results in there's a change of sign over here. So again, the convention where exactly you're placing the indices is important here because of the anti-symmetry. So this is one of the inner products that we can construct, and the other one that we can construct is on the other copy of the SL2C, which people usually denote by using a square bracket, which will be kappa tilde omega tilde. And I will just define this as being the contraction of the dotted indices. Omega tilde alpha dotted. And this, of course, is just this beta dot with epsilon beta dot alpha dot. So yeah, these are two inner products, and for people who have already seen a little bit about the use of twistors and spinors in writing down Cool expressions for scattering amplitudes, these are the inner products that are pretty much important. So I will comment a little bit about the Parquet-Taylor scattering formula, and it will basically be a combination of these kind of inner products. So kappa is a vector in C2. Yes, that's correct. Yeah, it is a spinor. It's a spinor. So spinors you can always understand as being these vectors living in C2, and the things that act on C2 are elements of SL2C. That's the thing. Yeah, sure. I think there's another question. No, there's not. Okay. Okay, so continuing on this, we can see again a little bit of the relationship between these spinors and vectors on space-time, on Minkowski space-time. So as I remarked before, so as we've seen, a null vector in Minkowski Is it notation without comment between the brackets? Yes, that's the usual notation. Yeah, I think you're probably thinking about the usual notation for an inner product. But like I said, this notion of this inner product should be a little bit more general. Because if you try to exchange one thing that I invite you to verify is that when you exchange these two things, you write omega kappa. This is you get a minus sign because of the way you contract these indices. In a usual inner product, you have when you change the position of the two vectors that you take in the inner product, you get the complex conjugate of the other. So usually inner products are linear in one of the arguments, anti-linear in the other. That depends on the convention. It is positive definite, and sometimes you ask for it for so the inner product of kappa omega is the complex conjugate of omega kappa. But not in this case. So in this case, it's a little bit more it's a little bit more general. So you might also take the absence of a comma here in this notation to remind you that this is not the usual inner product that you take on a Hilbert space. Yeah, or an inner product space. Okay. Okay, I struggle in where it lives the X alpha dot. So the X alpha dot alpha, it's just a vector. It's just yeah, it's just a way that we construct a vector. It is a two by two by two matrix. You can just think of it as being some sort of Hermitian matrix, which you can relate to points on spacetime. So they're not SL2C. They are preserved. The determinant of these matrices is preserved by elements by the action of SL2C. This is why you shouldn't think these as being some sort of points in some at least for now. You should think of them as being the points on some complex space. But we will coordinatize the Twistor space using these guys. But these are not the SL2C elements, if that's what you're thinking about. So SL2C are isometries of these products of the inner products. Yes, they are. So they are SL2C invariant inner products. So it means that if you act with elements of the SL2C, you shouldn't change. If you act with SL2C on each one of the entries of this guy, you shouldn't change the result of this inner product. Yeah. So a null vector in Minkowski, we wrote it as being can be written as a V null with two indices, alpha and alpha dot. So we wrote it as a, let me write it with kappa now, so you can see where we're going with this kind of thing. So if we have two null vectors, you can actually show that the inner product of them when you contract the indices correctly. So this is an exercise as well. If you take let me call this W null, you will get something like and let me write the W null alpha and alpha dot as being omega alpha omega tilde alpha dot. So this is just the product of those SL2C invariant inner products. So this is a part that is interesting, and this kind of thing is, let me introduce already the one of the motivations of thinking about Twistor theory in the context of particle physics, especially in the strong interactions, which is something called the Parquet-Taylor scattering formula, which is the following. So we consider this kind of formula is for n massless gluons. So when you have a massless particle, it is necessary like, the momentum. So if it's massless, the form momentum is null. So we can essentially write for each of these n, we can write the momentum, the momentum for a vector as being just the product of two spinors with opposite chirality, where this index I runs from one. Let me put this a capital N. So this runs from one to n. Sorry, let me be more. So it's just counting the number of gluons that go in at some process, and something happens, and then they come out. You're interested in computing the scattering process for this amplitude. And what Taylor found is that you can write down a very neat amplitude for this process, which is in terms of these SL2C invariant products, which would be something like this. So I will take this inner product over here. I will take it to the power fourth. I will have a delta function here, which is enforcing the conservation of the momentum of the moment of the particles. And then on the denominator, I will have a combination of somewhat a non-trivial combination, which is this is pi 2, pi 3, dot, 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 pi n minus 1, pi n, then pi n, and then we have the first guy again. Okay, this is. So this is the so-called Parker-Taylor scattering formula, and the fact that you can write these so simply in terms of these the spinor products is very interesting. As you all probably know, working in strong interactions is something pretty difficult. You can actually get this formula so neatly, and this is the actual thing that Nair interpreted in terms of twistors, which then led Wheaton to try to study to formulate a closely related theory, which is n equals 4 super Young Mills, in terms of a string theory living in the twistor space. So this is interpreted in terms of twistors and extended to n equals 4 super Young Mills, and then followed Wheaton derived in terms of string theory in twistor space. Something that I should also note, since I'm aware there are particle physicists in the audience, is that this amplitude you can only compute the scattering the contributions at tree level to the scattering amplitudes. This is not the full amplitude, so it's a little bit more complicated, but it's already something remarkable. You can do this even computing things at tree level with such a simple formula. All right. So, okay, time is flying a little bit, so let us continue a little bit. So I wanna go to a topic that is closely related. I'm a bit confused. Sorry. Okay, so there are two questions. Let me just bring this back over here because I think they're both related to this. So I'm basically confused by this formula. The form momentum has indices mu and pi. Pi has alpha and alpha dot indices. I'm sorry. Yes, you're absolutely right. Yeah. So as I said before, the mu all the Lorentz indices that you transform them as a pair of SL2C indices. So this should actually be like this. But this corresponds to one single Lorentz index. Yeah, yeah. Your question is totally valid. Um, but yeah. So rule of thumb is that you transform some Lorentz index as a pair of SL2C indices. That's the rule. Yeah, thank you for that. So what are the advantages of writing this in terms of spinors? Does it reduce the complexities, or can we compute the amplitude easily? Yeah, so this amplitude over here, you can in principle, well, you have like a closed formula for the amplitude at least at tree level. So I'm not really sure how people probably run this in the computer, but you have like a formula. So there's something that in principle you can with finite data, you can compute it in a computer. This is not given in terms of some sort of an asymptotic series or something that might take forever to converge or something like that. You have like a closed formula, and you have very few data. You have essentially some spinors that are related to the form momentum of the particle, because you are considering massless particle. You're just worrying about the kinematics of the thing. You're not necessarily worried about dynamics, and you just need you just need a conservation of momentum. So yeah, it is easier to compute it this way. Um, yeah. I'm not see if there. I'm not sure if this answers your question. But yeah, if there are no more questions, I'll keep on. So okay, so the next thing that I want to do is to complexify Minkowski space-time. And this is a general motto in twistor theory. Because the thing is that when you complexify things, you have all the machinery of complex analysis, which can pretty much help you out in defining things in a more general sense. And the thing is that what I will try to convince you here is that when you complexify Minkowski, you can pretty much treat more things than just Minkowski at space time, and depending on the notion that you have of a complex conjugation on this complexification. So let me write this down. I think it will be a little bit clearer. So we define the complexification of Minkowski, which is denoted by M with a subindex C of represented complex numbers, as being as C4, which just means that we got, well, remember that Minkowski was just R4 with some bilinear form. And we just took the entries, all the vectors, and we made the entries complex. If you do this because you have a four real component vector on R4, when you complexify it, you go to C4. So we do this and we equip it um, with some metric. Let me see how I denoted this on my notes, just so I won't make it any. Yeah, I denoted it as it as well. But now this is a holomorphic function of the coordinates in such a way that we will still have this kind of relation over here. So eta AB dxa dxb. And what I mean by this is just that this metric now is a function of just what the coordinates is not a function of x bar of some sort of complex conjugate, and each one of these vectors, has complex entries. So if I have let me write this. Dxa is just dx0, dx1, dx2, and dx3, and each one of them is complex. Okay. So, and if you think carefully about this, all the do we still choose a sign convention? No, that was that was the thing that I was going to say now. If you look at this a little bit carefully, because you have because you can decompose each one of these entries are complex numbers, and they're a combination of real numbers with with the I factor on one of them. The notion of a signature here loses a little bit of meaning. So this if you're always in a fight, which sign convention is is the better one to use in general relativity or quantum field theory, this is the more democratic the most democratic field that you can do, because they're all signatures are pretty much the same here. And one thing that you can do is pretty much you can recover the different signatures that you have in the real case by choosing a real slice of this complexified Minkowski spacetime. So I will show you now how to do this, but first I've seen that there are questions here. So we say that eta is holomorphic due to its non-dependence on the conjugate. What exactly a holomorphic function means? Exactly what you just said. If you have taken a complex variables um, or a complex analysis course, you've learned that a holomorphic function is something that is that you can expand in terms of a Laurent series, that you have it is differentiable. Um, and that satisfies the Cauchy-Riemann equation, that sort of things. This is pretty much the same thing here. We're doing like a number version in which we have we just mean that it doesn't depend, the function does not depend on the complex conjugate, but because recall that the metric it has a transformation law. When you change components on a metric, you need to include the derivatives of the coordinates. You'll pretty much end up with a particular case of that broader definition that you saw in a complex variables course. But yeah, here we will when I say a holomorphic function of the coordinates, I just mean it only depends on x. It doesn't depend on the complex conjugate of x. Okay, so good. Uh, but only two, so a question here, which seems to be an interesting one. Only two slices, the ones that give mostly plus and mostly minus, give physical meaning results. No, well, there's also Euclidean, right? So you might be bought. It really depends on what you mean by physical meaning. Because for example, if you're working in Euclidean signature, it's not very clear what you mean by a direction of time. And usually you need to impose some sort of periodic conditions when you're working in quantum field theory, but it's a useful signature to work in. If you ever taken a course in quantum field theory, you know that you can do make a little bit more sense of the path integral once you work in Euclidean signature, not in Minkowski signature, because in Lorenz's signature, sorry, because of the oscillating factor on the path integral. So you're usually worried about computing stuff that goes like an exponential of minus sx. So when you have this factor over here for the path integral, this is in the Euclidean signature. So this is a way to kind of make sense of the path integral measure, and to actually perform computations and obtain correlation functions. So from a physical standpoint, yeah, maybe you might have an issue with Euclidean signature, but it has useful computational value. So yeah, but good question. But even so, you can it is not well when working in theory, you do not always guide yourself in working with the things that have a direct physical meaning. So the fact that you can work in more general signatures here might be useful for from some other system that you can mimic that way. So in one of the exercises that I left on the notes, you guys are interested to find one of the a signature that is pretty much a plus plus minus minus signature that you can find by choosing a different slice. And this kind of thing over here, for those of you that are familiar with anti-de Sitter spacetime, you know that this kind of signature might show up in different contexts. So working with this kind of signature in Minkowski in like a flat space time, kind of thing is a good warm up to tackling the more general, the more difficult, the more challenging problem of working like a maximally symmetric and curved space time like ADS. So yeah. If you want a straight physical meaning, so yeah, you can recover only the Lorentz signature, but if you want to actually perform calculations, you need to recover at least Euclidean as well. So the way we do this, so how do we recover real Minkowski? So um, well, if you're living so let's think in simpler terms, right? When you're working in like a complex in the complex plane, if you want to take the set of z's of complex numbers which are real. So if you want z to be real, what exactly do you do, right? You just set it equal to its complex conjugate. So all the set so you can think of the real line as the subset of complex numbers such that it is equal to its complex numbers. So if you want to think about the real line as a subset of the complex plane, you can think about it this way. So every time we are interested in imposing reality conditions, which is what this is called. So these are called reality conditions. You should you should provide me a good notion of a complex conjugation, something like this, such that when I make it I make z equals to the complex conjugate of z, whatever the complex conjugation means, I should recover what I mean by real. So this is a more this is a somewhat of an abstraction of this usual notion that we have in the complex plane. I hope that's clear. So the way that we recover Lorentz signature is by, well, I define the complex conjugation as being of a x alpha and alpha dot. I would define as being the Hermitian. So if I write this explicitly, I should probably write x alpha and alpha dot again just for clarity. I'm sorry for erasing this, but so given x alpha and alpha dot equals to 1 over 1/2 of x0 plus x3, x1 minus I x2, x1 plus I x2, and x0 minus x3. Okay, so now I'm thinking about each one of these entries as being a complex number. I'm not thinking about it as being real numbers. So I can define the complex conjugate of this guy, which is just given, let me just not make sure I'm not going to mess up the signs. So this is just going to be the complex conjugate of this entry. So this is x bar 3. Here it doesn't change because this is just the diagonal part. But now we need to change the off diagonal elements. So if you work this out carefully, you will find this x bar 2. Oops, sorry. There's a minus sign here. I think no, I think I think there's probably one of these signs is probably wrong. I think this should be a plus sign over here. Anyway, You just get this by taking the complex conjugate of one another. So remember that, well, we can pretty much work this out, right? So if you take the complex conjugation of this guy over here, this is going to become a plus sign. This is going to become a minus sign. But when you change, yeah, and so yeah, this is correct over here that I've written down. Um, so yeah, so I should probably change this in the notes before I send it to you guys, so that you can work this out. Okay, now if I define this, I will get the Lorentz slice if if I make this equality, which is what we had in the beginning. So I said to you guys that if you construct this matrix out of R4 vectors, if each one of these components x0, x1, x2, x3 is a real number, then the matrix that you obtain is Hermitian, right? So if I impose this time, I just recover what I had for Minkowski spacetime. So it's not that fun, we already seen this, so it was pretty much the obvious choice. But something that also happens is that when you do this, you how can I say how can I say this? We can induce a conjugation on the spinors. So given, I'm going to write this as being a kappa equals AB. Let me put it this way, and omega is being CD. Then, what I will have, let me write this as with an alpha index, and we do this with an alpha dot index. So what I will get is that when I take the complex conjugate of this guy, which I will denote by a bar, I will change the representation that this thing is living in, and I will get an A bar, B bar, and the same thing with this guy over here. I will get an alpha, um, which will be C bar and D bar. I'm sorry. This should be a column vector, right? So because it is the conjugate transpose. So you go from a column vector to a row vector. Okay. So yeah. So this is kind of simple, but this kind of shows you this is an example how to recover a space-time in the signature that you want. So another more interesting example is the Euclidean signature, which I was commenting before. So the Euclidean signature, well, now I will define the complex conjugation as being something a little bit different, which will be, I'll keep this factor over here, but now I'm going to write x0 bar minus x bar 3, x bar 1 minus I x bar 2 minus x bar 1 plus I x bar 2, x bar 0 plus x bar 3. So if we compare, let me unzoom this a little bit so you guys can see. So well, if you try to compare each one of these conjugations, you see it's slightly different. You cannot get you really cannot get from this to this by doing some sort of simple matrix manipulation. So it's some sort of thing that you come up with, and when you impose the reality condition that I mentioned, that means just setting x alpha bar equals to x bar alpha dot. What you get is that this guy now written in, when you will get it will be written in terms of x0 plus I. There's a factor of y now. I y1 plus y2, I y1 minus y2, x0 minus I y3. And you can work this out. This is an exercise to show that you obtain this form. And the y's just happened because I've taken take xj equals to some z x, some real zx plus I y j, where j is 0 to 0, 1, 2, 3. So when you do this, when you force this equality, the z's essentially cancel each other. The real part cancels each other. You're only left with this imaginary part. So yeah, and what happens is that if you compute now twice the determinant of this guy, this is also a little exercise that you can do. You find x0 squared plus y1 squared plus y2 squared plus y3 squared, which is just a Euclidean metric. Okay. So are there any questions up to this point? I guess there aren't any. So as in the Lorentzian case, where the recording will be available. So this is a little bit of an issue because we're recording to the cloud, and the folks from ICTP are the ones that have access to this. So we will try to make them available as soon as possible. But by the end of the school, you should have all the recordings on. We'll upload it to some YouTube channel, and then we'll post the link on the other website. Yeah. Okay. So as in the Lorentzian case, this sort of conjugation induces something on the spinors. So the induced conjugation really means that and then you can work this out for yourself. So if you take this, you will get minus b bar a bar and sorry omega to the hat with an alpha prime of the alpha dot. Sorry, is this kind of vector. Now, something that you should be mindful and something that you can try is that if you try to take the hat twice on for instance kappa, you do not get kappa back. So this is not true, which is a little bit different of a usual complex conjugation that you think, right? Because when you apply the operation of taking the complex conjugation twice, you get back to the original number that you had. But not in this case. You actually need to, and this is also an exercise that you show that you need to apply 4 times to get back. And for people that are interested in this kind of thing, this is this is called a quaternionic kind of conjugation because it has some sort of relation with quaternions, and but yeah, this is something interesting that happens. So, question: the relation in this case between both signatures lies on the requotation of x0. So I guess your question is about the relationship between the Lorentz signature and the Euclidean signature. Yes, you'll get when you at least when you're working in Minkowski spacetime, when you're working in flat spacetime, you usually can rotate the time component to Euclidean space and work in imaginary time, so you can perform your calculation, and then you can your correlation functions, which are your observables, when they do not depend explicitly on time, you can pretty much rotate back and then give it like a sensible physical interpretation to them. But yeah, the relationship between the both signatures in quantum field theory is by a rotation of the time component. Yes. All right. Um, what else do we have? So yeah, and then I also left an exercise on the lecture notes, which is just to write it down, is that I want you to consider this complex conjugation, which is defined by um, x zero, oops, sorry, 0 bar plus x bar 3, x bar 1 plus I, x bar 2, 1. So I want you to, consider this kind of complex conjugation. You demand that, so impose that x alpha alpha dot is equal to this complex conjugation, and then see what kind of relationship, what kind of signature, metric signature that you get, and so if you do this, what is the signature, and what is the action on the spinners? So when you do, so if you do this, you will find something of a split signature that I was commenting earlier. You will find something like signature like this, and it imposes a very interesting relationship on the spinners. Namely that they will have to be real spinners. So I'll leave you. I'll let you guys try to figure this out, and you can, it is. It would be interesting to think about other complex conjugation that you could possibly take. I think these are pretty much the only ones that you can take on Minkowski spacetime, which are non-trivial conjugation. But you're free to try to exercise your creativity to figure out the other things. And of course, when you complexify more general spacetimes, you have even more possibilities of taking the complex conjugation of each one of them and select the real slice that you want. Okay, so in the remaining time, I will finally tell you guys. So what you all came here for, I will finally talk about the Twistor space. So um, the the idea that we will be working here, so the Twistor space, we will define it as a subset. So we usually write it down as being a PT. You know, this nomenclature comes from because when these things were created, they were actually called a projective Twistor space. So the PT stayed by, P for projective and T as Twistor. Um, and this is constructed as being a certain subset of what is called the three-dimensional complex projective plane. So this fellow over here, how you obtain this, and so most people have never seen like a projective space in their lives. So, but the idea is not complicated. So you just take C4, the space with four component vectors with complex entries, and you coordinatize with some set of coordinates which are homogeneous, um, stuff like this. So where each one of these numbers is a complex number, and then you impose a an equivalence relation, which is just given by, if I multiply this guy by a non-zero complex number, I should get ZA back. And for all R in non-vanishing complex numbers. There was a question. I think I heard someone speaking. Well, I guess I'm just hearing voices then. But yeah, so this is the kind of thing that you do, and this is just a notation for complex numbers without the origin. And so if you do this, this kind of thing is very hard to visualize because it's already hard to visualize like a C4 in your life. But if you want to if you want to see an interesting way to try to visualize this, you can look for the projective real plane. So something like, sorry, R P1 and CP1. And they're interesting ways to visualize it that you can check out in Nakahara's book as well. Um, over there they have some sort of ways that you can think of them as being patches that you glue in different ways. So, sort of like when you construct like a Mobius strip or the Klein bottle or stuff like that. There was a question in the chat. So are the indices one, two, three, and four? Yeah. Oh, so yes. Yeah, you're absolutely right. Thank you. It's the four over here. Yeah. Thank you. Each one of the entries. And so yeah, so you coordinate these things, and it's kind of hard to visualize. So you can, it's useful to think of these things in a more abstract kind of way rather than trying to intuition your way out through this thing. Um, so just because my computer's battery is about to die, and I don't want to disappear. Okay, there we go. So. And the way to obtain the tracer space is that we are going to use those spinners that we have before to coordinatize the space. So we will actually take the coordinates on C4 or rather on CP3 as being just given by two spinners of opposite chirality. So this is nothing to be afraid of. Spinners deep down, they're just two component complex vectors. So you're just writing this vector as being like some sort of I'm writing this as a row vector, but it really depends on your convention what you want to do. But this is just a something that has two components in one SL2 representation and other two numbers in the other representation. So this is just a vector with four entries, and the four entries are complex numbers. So it's nothing scary or anything. Why is one index up and why the other index is down is just a convention. Usually you take because you want to be able to contract something like this, two indices of the same type. So you write them in this way, and when you take the complex conjugate of the other, so if you want to do something like this, you should get something like a bar, and then you raise up the index and change the representation so that you can be a little bit more consistent when you're contracting the indices and where you take slices or anything. So this is just a choice. This is a choice that I've made. But it turns out to be a good choice, to actually coordinatize what we will be calling the twistor space. So yeah, I do this. So I prioritize this way. But furthermore, I put a constraint, which is called a incidence relation, which is just that I don't pick any pair of two components of vial spinors. I pick one that satisfies this relationship over here. So I have. So if I look at this, so I've written this in a very suspicious way because this I was using this notation to represent to represent the point of space time, right? So we saw that we can represent the point of space time as a 2x2 matrix, which I denoted this way. But if I only hand it to you this set of coordinates, I haven't told you anything about space time. I'm just trying to find a coordinate patch for the complex projective plane. So this is just a linear coefficient as far as I'm concerned. But it will turn out that this choice when we identify this linear coefficient as an actual point in space-time will give us the Twistor correspondence, the correspondence between points in space-time in Minkowski space-time and points on, or rather lines in Twistor space. So let's see how exactly do we do this. So if you look at this, so again, forget a little bit about Minkowski space-time for now. There's a question. Okay, yeah, it was just answering the other question. So just let's think of this in terms of a linear coefficient. So let's do a simple case again. So if we had, for instance, R2, the real line, and if I define a function on R2, if I'm coordinatizing this guy by a pair which I denote x and y. If I define a function, if I define y as being ax, so some linear function of x, what I'm essentially doing is that I'm picking some line that is passing through the origin with some inclination that is given by the linear factor on this equation. So what I'm essentially doing is that when I take the real plane and I take the sort of relation, I'm introducing a line. I'm picking a line inside this R2. So if you take this picture and you try to abstract your way into this sort of setting, what I'm doing is that I'm picking a line. I'm picking a line inside of CP3. And this actual line, I'm putting in quotes because, well, this thing is higher dimensional, right? This is a two component vector. This is also a two component vector. This is a 2x2 matrix. So something higher dimensional. And in fact, what this actually is what this equation here defines is actually a CP1. It's a Riemann sphere. So when I impose this constraint on the coordinates that I have on C4, what I'm actually doing is that instead of embedding a line as in this planar R2 case, I'm embedding a CP1, a Riemann sphere, linearly inside the CP3 over here. So this is something interesting, this kind of relation. So when I'm making this choice, what I'm doing is inserting this Riemann sphere, and because of this analogy with this two-dimensional case, we call these Riemann spheres lines. So these are lines, and I will write them now as a capital X. So you should understand this. So what did we do? We started up with a complex projective plane. We chose to coordinatize it using these Weyl spinors, these two component Weyl spinors, and then we tie them up together using this incidence relation. And by doing this, we have selected a Riemann sphere inside this CP3. Okay, so. And in fact, you can. I'm not going to go a lot through this, but you can pretty much show that any embedding of a Riemann sphere in this in this projective space, you can put in the form of this incidence relation. You can check out the notes for the details on this. But I want to but I want to give out the physical message of all of this, because see, like I said, you have treated this linear coefficient here as being just some coefficient, so just some 2x2 matrix which selects some subspace of the projective space. But if you interpret XA of a problem as a point in space-time, then this means that a line, again, a line meaning a CP1 in CP3, and now I'm going to talk about I'm just going to write it as being the Twistor space, because I'm just the Twistor space is just going to happen to be some subspace of the projective plane in which I impose some conditions that I'm gonna talk about in the next lecture. But it's this relationship still holds inside of PT. So PT is just a subspace, it's just a subset of CP3. So a line in this is corresponds. So it's equivalent. Well, not equivalent. Let me be more precise, but it corresponds to a point in Minkowski spacetime. By this relationship, by this incidence relation here. So this is part of the problem, the original problem, philosophical problem of working in twistors in general relativity, because now you're taking a point, which is something localized, which is something which is a very local concept in general relativity, and now you're substituted by something that is highly non-local. So if you try to, if you're trying to make a correspondence between Minkowski and some other more abstract space, you would, in principle, want some other things, local things that are going to local things. But that's not the case here. A point became a line in the other space time. So this is part of the non-local flavor of twistor theory. Now, you could pretty much ask the converse question. So, and then I will end up the lecture. So the converse is what does a point in PT correspond to in Minkowski? What happens to the line if we choose a signature? You mean if you impose a reality condition? Ask me on the next lecture. That's what we're gonna do. We're gonna see how imposing reality conditions on the twistor space affect the elements inside. Yes, that's a natural question to ask. So that's a question. And the way to think about this is that we should think about a point, like we do. How do we define? How can we define a point in two dimensions, right? So you take two lines, and then you take the point that they intersect as being a point. You say, okay, a point in the planes where two lines coincide. So the same thing is we're going to do pretty much the same thing on this set. So we're going to take two lines, x and y, and we define the intersection of these two lines as being the point in PT. So in the same way in this picture that I drew here on the side. So if I do this, what does it mean for the intersection of two lines? So recall that that we were coordinatizing the points, the points in this space by this using Weyl spinors and then using the incidence relation. So when we do this, what we actually mean is that we're taking some coordinate here, and it's equal to this guy over here. And I'm also taking, the set of coordinates which are equal to this guy, where x and y eventually they will represent different points in Minkowski space-time. So if I do this, I can just basically, put the quality, subtract both of these relations to find. So we find that x minus y alpha alpha dot contract with lambda alpha is equal to 0. Now, how can this? What does this mean? Well, we have two options, right? Either x, either lambda alpha is equal to 0, which is not a very interesting case. You just you want these to work for a general set of coordinates that you pick. But the thing is that you can write this relationship in a more suggestive manner, which is this is equivalent to writing, making the metric explicit. And now you have some matrix multiplication that makes it a little bit clearer what you should do. Because, well, recall again that this guy is antisymmetric. So the way, if you try, because you have an antisymmetric tensor, when you have antisymmetric tensor that is responsible for the contraction of the indices, what happens is when you contract a vector, the indices of a vector with itself, it should be equal to zero, right? This is the magic about of when you have anti-commutative things. So people who have taken quantum field theory and saw the Grassmann variables, you have stuff that anti-commutes. This implies directly that when you take the square of something is equal to zero. And by consequence, by anything that is proportional to that original thing. So this relationship over here forces us to say that x minus y alpha and alpha dot should be proportional to lambda alpha. Because again we're contracting it with this lambda alpha over here, and it's equal to zero. So either lambda is equal to zero, or this guy has to be proportional, because then you will have a relationship sort of like this. You're taking the square of some anti-commuting variable, and the anti-commutation comes from exactly the contraction with this anti-symmetric tensor. And because we have a leftover alpha dot index over here, we might as well write this as being proportional to a lambda alpha and lambda tilde alpha dot for some lambda alpha dot. But we saw that every vector that we can write in this way is a null vector. So the conclusion is that x minus y is a null vector. So a point in Twistor space corresponds to no separated vectors on Minkowski space-time. So as we will see on the next lecture, there's a very close relationship between the conformal structure on Minkowski spacetime. That means that the structure defined by the light cones with the points on Twistor space. With reality conditions that you impose on Twistor space. So this again gives a little bit of a flavor. So let me just write the final thing, the message, the takeaway message. So a point in Minkowski space-time corresponds to a line in Twistor space while a point in Twistor space corresponds to a null vector on Minkowski. So if you understood nothing about the lecture today, this is the message that when you're revising the notes or taking a look at the bibliography, this is the message, this final message that needs to come as natural as possible for you, so you can follow the next lectures. So yeah, for today, this is enough. I'm gonna stop sharing my screen and let me. Okay. So I'm gonna stop this, and I'll stop the recording. If anyone else wants to ask any more questions, I'll be happy to take them. Otherwise, I'll see you everyone tomorrow. So let me stop this.